Okay, so let's get started with our very first slide. And what I've got here is a very important question, which is what is important to you from a particle sizing technique? I'm sure you all will have your own ideas about this and can easily put together a wish list. The question is, which sizing technique is going to work the best for your listed needs? As you know, there are many different sizing techniques available. And what I've done here, I've listed most of them, and you'll probably recognize them all and may even have them in your labs and working environment. So what do we have? We've got a couple of ensemble techniques. These are where particles are all mixed together in a chamber of different sizes. The particles all fitted together in one chamber. Followed by, we have here counting and imaging techniques. And then further down here, we have various separation techniques. So I think at the end of the day, all of these techniques are complementary and they have to be used together to give a complete, true picture for your particles. I'm not going to say one is better than the other. My objective of this webinar is to focus on centrifugal sedimentation only and highlight its key features and benefits, and also talk about some of its drawbacks. I think sizing can be a little like trying to get a full picture, say for example, of this elephant we have on the slide. You might find one technique, if all it did was focused on the tail, then you may end up thinking that you actually got a snake. Likewise, another sizing method may only show up, for example, if it's focusing on the foot or the leg of the elephant, you might think it's a tree bark. Another could be looking at the trunk, making you think it's a hose pipe. And if we're looking at the ear, we would actually get mistaken for a large fan. Now, obviously, all of these solutions are correct, but just like a jigsaw puzzle, you have to piece together all of these solutions to see the complete picture. I think the important message I'm trying to get across is that it is important to understand that the best choice of sizing methods depend upon the nature of the sample and what characteristics of the size distribution are most important to you. And don't forget, one method can never suit all samples. You may need to use more than one method to see the full picture. Okay, fantastic. So let's move on to sedimentation. Sedimentation itself of particles in a fluid has long been used to characterize particle size distribution. What I've got here is Stokes' law, which is used to determine an unknown distribution of spherical particle sizes by measuring the time required for the particles to settle a known distance in a fluid of known viscosity and density. And with this Stokes' law, what you will see is I've got various different parameters, and if you know these values accurately, then you can actually determine the particle size diameter. Sedimentation can be either gravitational, which is one g-force, or it can be centrifugal, which is many g-force. When you are using centrifugal sedimentation, you do have to use a modified version of Stokes' law. So basically, if you know all of these values accurately, you can derive size data. And by introducing a known traceable standard, the timescale can be calibrated to particle size, and everything else can then be left as a constant. Now, there are two common sedimentation methods. The two are called integral and differential. Integral is the oldest of the sedimentation methods. And what I've got here to illustrate this is I have a column, a beaker, full of particles and fluid. And you see these double line. If you imagine you have a light source at one end of the column and a detector at the other end, the light source is traveling through the chamber, through the fluid and particles, and to the detector. So if you start off with a chamber full of or filled with fluid and particles, the detector beam at the bottom will pass through the fluid and measure particle concentration. The initial intensity of this source reading at the detector will be low. But as particles settle, big ones settling first, smaller ones settling later, the concentration of this dispersion will fall and the intensity of source reaching detector will increase. The result of this analysis will give you an integral plot because the sum of all the particles smaller than a particular size is being continuously measured during the analysis. Now, there are various problems with this type of sedimentation. I won't go through all of them, but the significant ones are the conditions of the analysis are very difficult to characterize, including any change in fluid temperature. And also the chamber must be emptied and cleaned following each sample. So you can't run samples after samples, and also you cannot run a calibration standard in between. So moving on to the second technique, which is the main one that I'm going to be focusing on in my talk, differential centrifugal sedimentation. Here, the sample of particles to be analyzed is placed on top of a column of fluid at the start of the analysis. You will see that the particles will sediment. The big ones are sedimenting first. The small ones are sedimenting later. Here, the intensity of the source, the signal, is high at 0 time, but as particles sediment and go in front of the light source detector, we reduce the light reaching the detector. So we were simply doing a very simple light measurement, attenuation of light, and this is going to give us particle concentration. We also are using this to measure the time taken for the particles to reach the beam. By measuring the time, and provided you know the density of the particles, you can calculate the size diameter. When a monochromatic light source is used, we can use me-light scatter theory, and we can apply this to the intensity data to calculate particle concentration. A plot of the concentration against the calculated particle size diameter produces a differential plot. And where only a tiny part of the distribution is being measured by the detector beam at any time, hence a differential sedimentation plot. Okay, so let's talk about sedimentation. Particles that are different in density from the fluid in which they are suspended will sediment at rates that depend on these following factors. So how can we increase sedimentation? What factors affect sedimentation rate? The most obvious one is gravitational field strength. Now, so far I've been talking about a chamber, a beaker, a column. In the current instruments, which offer DCS, we have a vertically held hollow disc, which is spun by a variable motor. And based on the disc speed, we can achieve different gravitational field strengths. We can achieve disc speed up to 24,000 RPM, and that creates a G-force of about 29,000 at the edge of the disc. The higher the G-force, the greater, the faster the sedimentation rate. The difference in density between the particles and the fluid would also affect the sedimentation rate. And as you'll probably understand, if you've got particles where the density is close to the fluid density, then the rate of sedimentation will be slow. And vice versa, particles with high density will flow through very quickly. The fluid viscosity affects sedimentation rate, and so does particle size and particle shape. So let's now move on to talk about differential centrifugal sedimentation, and I'm going to sort of use DCS from this point onwards. Differential centrifugal sedimentation is certainly a mouthful, and yeah, I always struggle saying that. DCS is a novel and innovative yet simple technique which has become reborn in recent years. Previous limitations and difficulties with the technique have been overcome using recent advances in technology and some smart thinking regards instrumentation and disc design. As I mentioned, we don't use a column or a beaker, but the most common design for DCS instruments is a hollow optically clear disc, which is driven by a variable speed motor. DCS is now a very powerful tool in measuring nanoparticle distributions down to 2 nanometers in size. So the practical range is anywhere from 2 nanometers up to 50 microns, dependent on particle density. So the general rule of thumb here is, if you want to achieve particle size measurements below 10 nanometers, you have to have particles with density greater than 10 grams per centimeter cubed. If your particle density is close to the fluid density, as you would expect with most polymers, then the size limit is a little bit restricted and you're going to be in the region of 20 to 40 nanometers as your lower size range. If you want to go up to the upper size measurement, the maximum size values you can achieve is about 40 to 50 microns. Again, the particle density would be very close to the fluid density. Okay, so let's move on to how to prepare the instrument for analysis. The technique itself is very easy to set up and use, and we simply need to follow 4 simple steps. Number 1, we set the disk in motion at a constant speed, which is based on particle size and density. Secondly, we fill the chamber with a density gradient fluid. We don't use water, we have to have a density gradient fluid, which I'll explain in my next slide. Thirdly, we inject a calibration standard. And finally, we run our samples. A single fill of the chamber normally allows us to run 40 samples before the disk has to be stopped, cleaned, and refilled. Okay, so let's come back to this big question. Why do we need a density gradient? Why can't we just use water? Well, DCS requires a slight density fluid gradient inside the moving disk to ensure that no instability develops during sedimentation. This instability is sometimes called streaming. Streaming is settling of the sample as a bulk rather than individual particles. So basically what's happening is that these particles are sticking together, and rather than sedimenting and separating as individual bands, they actually sediment as a bulk, and you will see a broad peak instead. So in terms of a gradient, what do we mean? Well, the gradient fluid must be compatible with the liquid in which the sample is dispersed in. So if you were, let's say, talking about a sample dispersed in water, we would typically use sucrose solution. The most common and simple gradient is done with sucrose. And what we can do is we can include different components into the gradient. So if your sample is dispersed in a fluid which had certain dispersing agents, salts, buffers, we can actually include that into the sucrose fluid to make sure it's compatible with your sample. I must add that this gradient does not last forever and will degrade with time. And that's because there is molecular diffusion of the components in the gradient. Plus there's physical mixing as well. A typical sucrose gradient would last 6 to 8 hours, which is still enough for a day's work. If you were to use a higher viscosity gradient, let's say if you made it up using dextran, then you would get a much longer gradient shelf life, possibly up to 72 hours. Now, we're not just restricted to water-based gradients. If your sample is in an organic fluid, we can also use organic solvents as well to make up our fluid gradient. So, how are these gradients constructed? The answer is very easily, very simply actually, and there's 2 methods of doing it. We can actually use an automatic gradient builder, or we simply make up a series of manual injections of gradually decreasing density fluids using a syringe and needle. In both cases, all you need are 2 fluid solutions, a low and a high. So in this example, we've got 8% and low and 24% sucrose solutions. You simply make up two solutions and you inject both of these in different quantities into the moving disc. The nice thing here is that this does not have to be done very accurately. So it doesn't really matter if we don't have an 8-24% sucrose, we could have 6-18, for example. It doesn't matter. The reason it doesn't matter is because we are always calibrating after we make up a gradient. What we have to remember, the raw data is simply time versus absorption. By running a calibration standard, we can convert the time axis to particle size. A calibration is a standard of known size, a known density, and is traceable. We can run a calibration in between every sample, or optionally, you may decide to run a sample in between every 1 to 10 samples. The more times you run it, and certainly if you calibrate before each analysis, that will give you the highest level of accuracy and repeatability. Okay, so let's have a look a little bit further about running samples. And here I've got a diagram. It's showing a front face of the disc. What we've got here, the front face of the disc, as I mentioned, is hollow, optically clear. We've got the blue area, and I'm just trying to get my mouse to work. This blue area is our fluid gradient. The inner edge is representing our low density fluid, so let's say 8% sucrose. The outer edge of the fluid is representing 24% sucrose. And we have a simple gradient from 8 to 24, a linear gradient from 8 to 24 from the inner to outer edge. The light source detector is actually sitting on the edge, which you can see by this vertical blue line. It makes it a little bit clearer if I show you the cross-section of the disc. So this disc is being rotated here. This is the axis of rotation, and you can see that the disc is in between a light source and detector. The light source we're using is a monochromatic light of 405 nanometers. The reason we've gone with this short wavelength is because it gives better detector sensitivity when particles are smaller than 100 nanometers. Okay, so what we do is we take our sample, we inject it into this central enclosure cap. The sample strikes the back inside face of the disc, and it spreads out radially to form a thin film on the fluid surface. If we have a sample dispersed in water, the water will sit on the fluid gradient surface, and the particles, as long as the density is greater than the fluid, will start to sediment out and moves radially as a band from the surface to the outer edge. At some point, these sample bands will separate, go past the light source detector, and finally end up on the outer edge of the disc. When the analysis is complete, the sample will remain on the outer edge because the disc is moving. So you can then inject your next sample without worrying about any contamination from the previous sample. If you look carefully here at this bottom right-hand corner of the slide, you will see a diagram showing separated bands of particles which are moving through a gradient. And we can see separated bands down to 2% difference in size. What's really important to understand is this is a chromatography technique, a separation technique with the ability to separate down to very small difference in size. So what kind of information can we get from such DCS analysis? Well, the two important analyses is one, we can get absolute particle size measurement, and for that we would need the following. We measure the sedimentation time, we need to know the particle density, and we would also need to know the density of the fluid gradient. Obviously, because you know the gradient you're making up, you would have that information pretty well defined. And of course, we need to know information about the calibration standard. If you wanted to get absolute weight and number measurement, then it's important to have available the optical parameters of your particles and fluid, meaning we need to know the refractive index. We also need to know the absorption parameters. And what this gives us is the particle's effective scattering cross-section. Now, mean-light scatter theory only is true for spherical particles. So when you work with non-spherical particles below a certain size, we do need to add a non-sphericity factor into the equation to correct the inaccuracies that the weight and number measurement values may give. The number distribution is calculated based on simple geometry. Great. So occasionally we do get users which come up, who have samples which have a very broad dynamic range. So typically, I'm going to think of this example here where let's imagine you have a sample. You've got some very small particles, some fines in there, let's say 20 nanometers, and you've got some very large particles going up to 20 microns. How are you going to analyze this sample? Because if you use a fixed speed, it's not going to work for both ends. A slow moving disk is great for the big particles, but the small particles will take forever to sediment. And vice versa, if you use a very fast speed, great for the small ones, but the big ones will just fly by without being seen. Wouldn't it be ideal? Wouldn't it be great if you could ramp up the speed somehow, where you start off the disk very slowly, separate out the large particles, and then ramp up the speed to its maximum speed to separate the fines? Would work fantastically. However, the problem you find is that if you change the disk speed, this will cause disruption of the density gradient and it would become unstable. This has all got to do with turbulent mixing and the fact that the fluid does not move at the same speed as the moving disk. How can we overcome that? Very simple solution. We can actually place some special speed ramping inserts or baffles inside the disk, which will allow the disk speed to be changed without disrupting the density gradient. Now, I'm just going to skip to this slide to show you what these baffles look like. These are baffles, they come in pairs, they're T-shaped, they're placed inside the disk at opposite ends, and what they do is they partition the disk. They partition the disk in such a way that they make sure that they cause the fluid inside the disk to move at the same speed at the disk. So it's kind of a separator wall which prevents the disruption of the density gradient. So a very simple way of allowing you to measure particles of very large dynamic range. So we can do analysis of dynamic range of up to 1,000 quite easily. Another requirement is where you may need to measure particles where the density is lower than the medium in which they are dispersed in. So, for example, let's say you are looking at oil dispersion droplets in water. If you're trying to do this with a standard disk, as you can see, these particles will simply float on the surface. Now, wouldn't it be great if somehow you could inject that sample to the bottom of our chamber, or if you're looking at a disk, if you can inject it at the edge of the disk, so that rather than sedimenting, these particles will float from the outer edge of the disk to the center of the disk. And we can actually do this with a special disk design. And we have a special disk called a low density disk, which can do exactly what I've just said. What we have here with this special disk is that we have a very special groove which is machined onto the front face of the disk. So I'm kind of just showing you that with my cursor. And this particular groove has got 4 capillaries, 1, 2, 3, 4, as you can see, which connect this groove radially from this position to the outer edge. What you do is, rather than injecting your sample inside towards the center, you inject it with a special injection port into this particular groove. The sample then spreads out, or it moves down these 4 fine capillaries, and it ends up on the edge of the fluid gradient. The sample then moves from the edge towards the center. The only thing you have to remember to do is make sure the light source position is moved from the outer edge to the inner position. Okay, great. So I've kind of covered the technique, I've talked about how it's set up, and I've given you some examples of special disk designs. Let's move on to talk about some of the type of applications we can use DCS for. Now, the bottom line is that DCS can be used for any samples as long as you have a dispersion, and the kind of applications are quite wide. I've listed some of these, but as long as you have a dispersion, it will work very well. So what are the key features and benefits? I'm going to go through some of these very quickly. The most important benefit is the ultra high resolution capability, the ability to detect and measure and resolve peaks which differ in size by little as 2%. And what I've got here as example is a polystyrene mixture. I've got 9 samples deliberately mixed together, and you can quite clearly see in this distribution that we can separate all 9 peaks and size them accurately. We can see weight on the y-axis and particle size on the x-axis, but clearly we have resolved those 9 peaks. If you try to do this measurement, say with an ensemble technique, BLS as one example, you will find that these six peaks in the middle will not be individual peaks, but you will end up with just one broad peak with a mean particle size measurement. And the same would go with these 2 larger particles. The DCS technique is great for resolving aggregates and agglomerates. And so we can detect and measure, quantify multiple particle peaks. In this example, with an adenovirus sample, we've got a dirty sample, which is shown by this red trace. And you can quite clearly see that we've got some aggregates. We've got a tail showing some large agglomerates. And as we purify this sample, we end up with this blue trace, which is our clean sample. So the technique is excellent for following the purification, as we are seeing in this example, and for detecting such multiple peaks. The technique is also extremely sensitive, so we can detect and measure very small and subtle changes in size distribution. So if you're looking at small additional peaks, we can see them. Here in this example, if you look at the main distribution trace, you will see that we see a broad peak, not very exciting. However, if you look here right on the baseline, although it's not very clear, if we were to zoom into that, you actually will see that we've got an additional peak at a larger size. And it's actually sometimes this peak which is more important than the large peak here, purely because that small additional peak could be, for example, a pigment blocking an inkjet nozzle. So having the sensitivity is critical for showing up these small subtle changes. Okay, this certainly is my best slide. I love talking about this, and those who may have heard my presentation before will have heard me talking about this with much enthusiasm. What I'm trying to do here is demonstrate how the technique is reliable, accurate, and reproducible. What we've done is, in this example, we've taken a PVC mixture and we've given it to 5 labs to run. So we're looking at running this sample on 5 different instruments which use DCS as a technique. If you imagine the variation between all of these 5 instruments, they obviously will have a different user. Different instruments, different disk speed, obviously different conditions in the disk in terms of the density, the viscosity, the temperature. I mean, I really could spend ages giving you a whole list of variation. However, we run the sample, we look at the results, we overlay all 5 runs, and what we end up with is, as you will agree with me, excellent reproducibility. How can that happen? Why is it so good? Simple answer. Regardless of how many variations there are, what conditions in the disk, because we are calibrating, because we're running a NIST traceable standard before our sample, this removes all of these differences. And so we always end up with real reproducible data. We can also do quantitative analysis with the DCS technique. So in this example I've got on the screen, we've got 4 gold standards clearly separated. So certainly that's showing us the resolution capability. But what I really want to focus on is this little table here. What we've been able to do is we've been able to determine the area underneath these 4 peaks and given it a percentage weight fraction. Now, we deliberately mixed 4 fractions of equal volume, and we can actually see with the weight fraction that we do have almost 25% of each. What's nice is that the software calculates the total weight of the particles that it has seen go past the light source detector. This can be very useful. For example, if you have accurately determined the volume of your sample, so if you used a graduated syringe needle and you know the absolute volume, from this number of the weight, you can actually determine the concentration fairly accurately of your sample. Okay, how does it work with non-spherical particles? Certainly particles with very high aspect ratios. And this example, carbon nanotubes, is a very good example I would like to talk about. Now, the dispersion of carbon nanotubes, as you may know, is very important to utilize many of the high thermal and electrical conductivity properties. During the dispersion process, agglomerated carbon nanotubes have to be broken down into exfoliated particles. Now, this degree of exfoliation and evaluation of the dispersal method can be assessed with DCS. We can see that very nicely here with this example here. We've got a very large peak showing us the agglomerated fraction, and we can also see this tail at smaller size, which is represented the exfoliated fraction. As we process the sample, we will be converting this large fraction into this smaller fraction. We also find the technique works very well to differentiate between different diameter carbon nanotube types. For example, if you had single-walled and multi-walled samples, that would also be discriminated. Now, there is plenty of work happening with coating of nanoparticles. Typically, these can be heavy metal nanoparticles, metallic nanoparticles for drug delivery applications, and you could be coating a polymer, a sugar, a drug, many different examples. Imagine here, we've got a gold citrate particle. It's about 13 nanometers. You are coating this with a polymer. Now, the difference in size between the core and the coated is going to be marginal. It will be very challenging to be able to see both particles with most techniques. The reason why DCS works very nicely to discriminate these two material types is because we're working on density differences, not size difference. Because by coating the gold, we're drastically changing its net density. And so when we run a mixture of these two materials into our fluid gradient, we will find that the citrate core will sediment out first, and then the coated particles will sediment out later. So you get this separation. And we can see with the blue trace that we can still identify and quantify the amount of uncoated gold. You probably look at this and say, well, how can a coated sample of nanoparticle be smaller in size than the core? Well, it's quite simple. We have to remember the calculation of the position of the peak is done by entering the particle density. We're using a density of gold. So this blue trace is not true density value. It's a core with the polymer coating. And so this position is incorrect. If we knew the density of the combined core coated particle, we could reposition that by recalculating the data. However, we do have algorithms present whereby if you know the density of the core material, if you know the density of the coating, you can actually use that to determine the shell thickness. Okay, coming towards the end of my presentation, I'm going to sort of finish with one last example, a very funny example. I do visit a lot of universities and I do run a lot of student samples. On one occasion, a student came to me and said to me, I've been working with silica particles for quite some time throughout my PhD. And I'm coming to the end, I'm writing up, and it'd be great if I can include your data into my thesis. I've been using laser diffraction and DLS. I've always seen one peak at 4 micron. We run the sample, And to the students' shock and horror, we were able to see this distribution. Now, firstly, we were able to show that there was a bimodal distribution rather than a single peak, which was understandable because we do offer high resolution. However, what was really quite shocking was this small peak at 0.5 micron. The student had never seen that. And in fact, I was told that this must be contamination from the disk. It must not be her sample. We ran the sample again, and we still showed this peak to be present. At which point, I was told that if you are going to send this sample, could you please take that out and actually cut that out from the distribution and just send me the distribution at the upper size range, because that would be quite hard to explain if an examiner picked up on it. One very important point really to make here is that, yes, this is a small peak. It's not very significant, but if you converted this into a number distribution, you actually will see that this is quite large, and you do have a lot of large number of small particles. And if you were to use a second method, such as SEM, you should be able to see all these particles. And you can quite clearly see here on this SEM that we've got two distributions. Well, we've got the bimodal here shown by these two large particles, and within the SEM image, we can start to pick up the very small 0.5 micron nanoparticles. Okay, fantastic. So what I've done here is simply summarized the main features and benefits of the technique. I'm not going to read through this. It's there for you to see. What I like to do, however, is also perhaps talk about some of the weaknesses of DCS. And the most obvious one is it's not really good for analyzing a sample which is unknown, which has a mixture of particles of unknown densities. Because what you'll end up is you could end up with a very broad peak or a multiple number of peaks, but there's no way of knowing which peak belongs to which sample. Also, the analysis time can be slow, especially if you're looking at analyzing particles which have very small size and where the density is very close to the fluid density. I mean, typically, a runtime is a few seconds to a few minutes. You would never run more than 60 minutes, 60 to 90 minutes, but yeah, you just have to appreciate that on some occasions, the analysis time could be slow. The DCS technique is not suitable for large particles because they will just, even at the lowest disk speed, they will just fly through or pass the light source detector without being detected. And fourthly, we do need density value to obtain absolute particle size diameter values. Now, sometimes that is not available, and in most cases that's not important. So certainly if users are doing a comparative study where all they want to see is, if I change the chemistry of my sample, what are the subtle changes in the size distribution? How does it shift? Then it doesn't matter as long as you use the same density value. If, however, you said to me you do need absolute size measurement, then there are various ways of doing this. You could always calculate and determine the particle size measurement or data. You could use a second technique such as SEM imaging to determine the size and then put that into the software to back calculate the particle size density. And thirdly, a very clever way is to actually run the sample of unknown density using this DCS technique by using two different gradients. So for example, you could run the sample on an 8 to 24% sucrose gradient and then repeat the analysis on a slightly different gradient. The position of those two, the position of the peak on both runs will be different, but if you need to align them, you simply go through different density values on both calculations until the position of the size peak is exactly the same on both runs, and the density value to reach that position then becomes the true density. This can be done with two different fluid density gradients using a standard disk, but also with low density samples, you can actually run the sample on a standard disk and also repeat the run on a low density disk and still achieve the same calculations. Okay, so far I've only talked about the technique. I'm just going to finally just show you a typical instrument that can be used for doing analysis with differential centrifugal sedimentation, and this is the CPS disc centrifuge. The picture I've got here on the screen is the latest CPS instrument, and many changes have been applied to this instrument. The most important one is the fact this is a UHR instrument, which offers ultra high resolution capability. The big difference between this and previous instrumentation is that the previous instrument had a vertical line for its light source. The new instrument has a narrow a modified detector beam, which is narrow and takes the form of a short arc. The idea being, if it's an arc, then it will sit better on the moving bands. The disc is also different. There's a new standard solvent resistant disc, which is made up of CR39 polymer, which doesn't yellow and is optically clear. The instrument comes with extra soundproofing and a double wall construction to reduce noise. And also recently a disc balancing module has been included into the instrument. And what this does, it ensures the instrument longevity by recording the unbalance and warning if the disc is outside its set specification. So what this module is doing, it's continuously measuring the disc imbalance, and it identifies which disc hole on the disc needs weight to be added and how many milligrams of weight to be added. So this means that over time, if your disc does become unbalanced, you can correct for this yourself. Excellent. So we are at the end, finally, of my presentation. I'm going to just now have a look at if there are any questions on the control panel. Yes, there is quite a few. I don't think I'm going to have the time, unfortunately, to cover all of these. Thank you so much for these questions. Maybe I'll just go through one or two of these very quickly. Someone's asked, can you collect the fractions? Yeah, how many times have I been asked that question? It would be wonderful if you can. Unfortunately, the answer is no. This is an analytical disc centrifuge, so there's no way to siphon off those fractions. So it's not a preparative system. We cannot collect those fractions. What if I didn't know the particle density? I think I've covered that over the last few slides. The other question I've got is, does it give any information on shape? How does it work on non-spherical particles? Very simple answer. Unfortunately, like with all techniques, we will only be able to achieve the weight equivalent spherical diameter. So it does not give information on shape, I'm afraid. Let's make this the last one. Sample volume and concentration. What do I need to use? Sample volume is typically 0.1 of a mil, and concentration is 0.1% weight per volume. So that equates to 1 milligram per mil. Okay, I'm being sort of flagged down. I'm sort of very close to my time spent. Thank you so much to everyone for listening on to this webinar. I hope you have found it interesting and informative. I should add that we're very fortunate to have one of these CPS disc centrifuge in our office currently. So if you're interested in running samples, if you're interested in me bringing the instrument to your site and doing a demonstration, please do let us know. Please stay in contact and let us know how we can assist you going forward. Thank you again. Everyone have a lovely day, and I hope to speak to you all very soon. Thank you. All the best. Bye.